My name is Joson Raber, and this is my coworker Jason Cheatham. We work for the Air Force Research Laboratory, specifically for a branch called the SPI, stands for Software Protection Initiative. And our charter or goals are to assess software protections, and the end result is to protect government systems. So to do that, to come up with good protections, the team that I lead is a reverse engineering team, and we really try to break those protections and understand how long a protection can hold from three different categories: tampering, reverse engineering, and piracy. Okay? And so today we're going to show you one of the tools that we use on assessing protections. We use a hardware debugger to walk through protections. Before I proceed, I got to state that we cannot answer questions in a public forum or go off our already approved script. Due to the public approval process, we must stick to the script that has been approved for public release. One of the hardware debugger that we do use is the American Arium, and we'll kind of step you through and show you how to use an ICE effectively, again, to break protections, and also to kind of give a nice tutorial at least, because when we were using it there was nothing, so it was trial by fire. Okay, so here's kind of the outline. We'll give you a kind of a hardware and software breakdown of what it looks like, the different types of breakpoints that you could use, some macros, and then how to use it to actually reverse engineer in a hypervisor.
So this is a photo of the American Arium ECM XTP3, which is just one of the more popular commercial x86 in-circuit emulators, or ICEs. The emulator is a little bit of a misnomer because it's not really emulating anything. It's just basically providing a JTAG port for you to use the debugging facilities built into the CPU. So, using that though, you can do all kinds of neat things like read memory, change registers, things you can do with normal debuggers, plus some really interesting things like completely stop the processor and look at things, without having to worry about protections interfering with you. So to use an in-circuit emulator, you need two systems. It's a little like a WinDebug kind of remote setup. You need a target and a controller. The ICE gets plugged into both of them. The controller actually runs the debugging software. In our case, it's something called SourcePoint. I'll talk a little bit more about that in a couple of minutes. And then you actually have to plug it into the motherboard. If you are lucky, you'll have a motherboard with a JTAG port on it that you can just plug this thing right into, and it's nice and clean and easy. But that's not really very common to find a commercial PC with a JTAG port on it. So what you usually end up having to do is use an interposer. And an interposer is basically a little shim that goes in between the CPU and the socket that takes the JTAG pins and routes them out to a JTAG port. And that works well enough. It's just, it's kind of expensive. It costs about 20% of the cost of the entire, emulator anyway. So the emulator is a $10,000, $11,000 piece of hardware. The interposer is another $2,000 on top of that just for this little shim. And they're a little delicate too. When you got a CPU with like a 500-600 pin ball grid array, you can't really be plugging it and unplugging it from that socket a lot. So it's a delicate little system, but it works. It's good. Yes.
All right, so there are some limitations to using like a kernel debugger like WinDebug or KDG for Linux. For example, with the American Arium, we can reflash the firmware, we can debug hypervisors, and also again walk through a lot more protections. As Jason said before, it's kind of a steep price to to buy one of these guys. Also, you need physical access. But one of the kind of neat things I found is, we're going to talk about some macros here in a minute, but you can write a lot of macros to work on. It's just an x86 essentially. So if we're reverse engineering some application on Linux or Windows, it really doesn't matter to us. It's just throwing on the system and then start debugging. It's kind of neat. Okay, so the point of this is just to kind of show you what the actual debugger looks like. As you can see here, you got both cores, so it can support up by 8 cores. Again, here's the memory, and you can modify this on the fly. You can even load anything you want, like a driver, right into the memory from here. Here's all the registers, and this is kind of the macro window. This is where, like I said, we talk about customizing it to make it a little more efficient and better, kind of like WinDebug. Okay, so let me talk about breakpoints. It's a little bit different than the normal breakpoints that we use for like WinDebug. And again, that's some of the point here is it uses the DR registers, but it has it sets a bit in a DR7. It's an undocumented flag, and when that hits, again, you just start debugging. But again, protections can detect this type of breakpoint. The software breakpoints work a little bit different than you're used to with like AliDebug or Immunity or GDB, where they're using CCs. In this case, they're using an ICE-BP breakpoint, and again, the DR7 bit 12 needs to be set. And again, then once that trap has been set, it will replace the F1 with the bytes that are stolen. You can start debugging. But the last one that we like the best is using an infinite loop. And you've probably seen, or a lot of you know what the EBFE is. It's a jump $, which again loops to itself, and you just need to steal 2 bytes. One thing that I found is, you just can't, you got to be a little bit careful when you're dealing with protections, maybe in malware or in software. You can't just throw an EBFE wherever you'd like, because then they can detect that usually through checksums. So you might have to be smart depending on what kind of protection you're looking at. So a lot of times we'll put it in the actual loader in Windows or in Linux. Put the EBFE there. As the application starts up, it'll halt, and, and then you can actually halt, or it'll loop, and then you just hit halt on the hardware emulator. You can replace the stolen bytes and then start stepping. We actually write little macros too that'll do those very things. And again, for timing checks, same thing. You can hit a macro that when it hits stop, it halts the actual the hardware halts the system, and then we can pull off the RDTSC or something along those lines, and then just start spoofing it. Another nice thing is like if you're debugging drivers or something along those lines, you don't have to figure out where Windows or Linux has loaded the driver and then do all the weird calc-based math, figuring out where the page table and the physical memory is. You just hit halt. Sometimes when you hit halt, be aware that there'll be a context switch maybe in the OS, so it won't hit in your EBFE. Just hit go and then hit stop again, and then you'll be right there. Okay, macros.
So a lot like other customizable debuggers, SourcePoint has a macro engine. You can write macros to do all kinds of things. You can automate tasks. You can implement different functionality like stealthy breakpoints. And in this case, for the case of the hardware debugger too, you can provide some OS some semantic kind of information, because by default the Arium system is very raw. You don't have, you can't, for instance, just list processes in the operating system or list drivers. You don't have access to structures like that, because by default, the controlling computer that's hooked up to the Arium, the only thing it knows about the target is that there's a CPU and memory. It knows nothing about what's in there, and so that makes it a little daunting at first to do anything with. And so macros can really help out there. The language itself is an interpreted, C-like language, a very simple, standard kind of imperative macro language. It's got all the normal kind of features, variables, functions, control flow, and a few hardware-specific things to like stop the emulator and start it back up again, set breakpoints. So this is a simple example script on the right. We have a little script that just illustrates some of the standard language features. We're defining a function. It takes arguments. You can type the arguments. Infinite while loop that's actually looking at the EIP register to make decisions about what to do. In this case, it's basically a memory range breakpoint. You call the function, you give it a start address, you give it an end address, and then you say go, and then it will basically just step until it gets into the proper address range and stop. It's it's not particularly fast. We're stepping 4 instructions at a time to make it a little faster, but it's better than doing it by hand and sitting there hitting the button over and over again. So this is just a real short video of this breakpoint running, just to give you a feel of how things kind of work in SourcePoint. Basically, you stop the emulator, it halts until, again, just like a regular debugger, tells you where you are. I used it in, well, you can't really read that all that well, can you? Well, anyway, so basically you stop it on an eBFE like Jason was talking about, an infinite loop. You put your bytes back, you type in the macro in the little, in the command area, hit go, it runs, and there you go. It does what you'd expect, and then it stops, and then you can start debugging. So, yes, also awesomely tiny text. This is, another example macro. In this case, it's like a run trace. And the macro language also gives you access to things like files. So you can open a file, you can, run a trace, and you can log information out to a file. In this case, we can also do things like try to avoid stepping through kernel code. Like the macro will actually pay attention to the address range you're in, and it says, oh, if I just step from user code into something that looks like kernel code just based on address range, well, set some breakpoints afterwards and go. Don't bother to step through kernel code, because even with the emulator, sometimes you'll blue screen your target. So the emulator access, like I said before, is pretty raw. You don't really have anything when you start out. You can't really do any of your generic debugger things. Like you can't just list processes and attach to one and start debugging it. So we wrote a whole bunch of little macros that are developed, in our case, for Windows XP Service Pack 3. They'll probably work with other XPs, but they're fairly specific because they're basically using a lot of forensic kind of techniques to look through memory and find structures, and those change a lot between versions of Windows. So, first question, when I opened this up was, how the heck do I attach to a process? And so, standard kind of forensic technique is to look for some known structures in memories, find the process list, and be able to walk through it, and then you can find the processes. And so, I wrote a listprocs macro, and that was basically my first step is, find these things. So if you look at them, you want to, also be able to change things. So there, we wrote a hook syscall macro, a get system service descriptor table macro. Similar things for drivers, because the emulator is really good for that, because again, you can do things like set breakpoints in the kernel or in drivers and not have to worry about things freezing, because you're sort of running outside the system. And so, I wrote like a list modules macro that, lists all the drivers. And there's we've written several other simple macros, but the idea is basically, you can use these simple macros to give this fairly raw system a lot of user-friendly functionality. So again, kind of a short, video that's basically, this is what we can do with macros. You load your macro library in the command prompt, you get a bunch of functions, again, like list mods or list processes. You can call them again. It's basically, just like doing it in all your WinDebug with custom macros. So just to look in a little more detail about what exactly we're doing with these functions, I'm going to look at the get syscall address macro just to show you kind of how we're doing this in this, with this emulator, how we're actually looking at the system. So in this case, we're going to have a top-level function, and it's get syscall address, because that's what we want to do. And you're going to give it a name, like nt-create process, and you want it to tell you, what's the address on my target system. And so, one kind of a main component in that is this function that's SSDT index to address. So we're going to get our name, we're going to get an index for it, and then we want to say, well, what's the address? So that works okay. That's just get a pointer to the base of the system service descriptor table, and based on your index, tell you what the address of your particular function is. That seems easy. But where do we actually get the address of the descriptor table? And that's, things start to get a little more interesting there. And this is where I was really digging through like the source code to volatility, which is a Python framework for doing forensics. So in that case, the Arium, again, you don't have exported symbols to look at because you're not really running inside the operating system.